We want a differential equation governing I of t for t greater than 0 after this switch opens at t equals 0. So to get a differential equation for t greater than 0, we look at the circuit for t greater than 0. We have a 4 amp source, we have a 12 ohm resistor, we have a 4 ohm resistor which is in series with a 2 ohm resistor if this switch is open, so I'll just combine those and make that 6 ohms. We have a 2 Henry inductor, and this is I of t. Now to find a differential equation, we need the voltage current characteristics of the inductor to get involved. We might as well draw those on our circuit schematic. Now to get a differential equation, we need to get the voltage current characteristics of the inductor involved. We might as well put those on the schematic so that we don't have to remember them later. So if this is I of t, the voltage is going to have its positive terminal there, and it will be 2 times di by dt. Now we just have to do KVL, KCL, and Ohm's law. Let's call this node A and do KCL at A. So if this is node A, this voltage I'm going to call V sub A. So we have 4 amps entering the terminal, which I'm going to call that a negative 4 amps, plus VA minus 0 volts over 12 ohms. If we call this our reference terminal, or 0 volts, plus the current through the 6 ohm resistor is just I of t is equal to 0. We've ended up with one equation and two unknowns. We need to eliminate V sub A, so we need another equation. Let's do KVL around this rightmost loop. So we get V sub A is equal to 6 ohms times I plus the voltage across the inductor, which is 2 di by dt. Combining these two, we get 4 amps is equal to V sub A over 12, so that's 1 over 12 times 6I plus 2 di by dt, plus I is equal to 0. There's a differential equation which contains only I as an unknown. Now let's check our differential equation by letting t go to infinity. We always want to check our results. An easy way to do that is to look at the steady state response. So if we let t go to infinity, this term is a constant, so I, as t goes to infinity, is going to become a constant. This term will be 0, so 4 is equal to I over 2 plus I, which is 3 over 2I. So I at infinity is going to be 8 over 3 amps. Let's take a look at the circuit. And as t goes to infinity for a constant input, the inductor will look like a short circuit. This is I of infinity. We know the current going into a parallel combination, so this is a current divider, so this is going to be 4 amps times the other resistance, 12 ohms, over 12 ohms plus 6 ohms, which is 2/3 of 4, which is 8 over 3 amps. And they check. Now we need to find initial and final values of I of t. For the initial value, we're going to rely on the fact that an inductor can't change its current instantaneously. So let's take a look at the circuit at t equals 0 minus just before that switch opens. While the switch is closed, this is a short circuit, a 2 ohm resistor, and the inductor looks like a short circuit as long as this switch has been closed for a long time. There's no voltage across the short circuit, so there's no current through this guy, and I at 0 minus is 0 amps. What we want is the initial condition, I at t equals 0 plus, but that has to be equal to I at t equals 0 minus because currents in inductors can't change instantly, so this is 0 amps. There's my initial condition. For the final value, let t go to infinity. We already did this on the previous slide, but 4 amps, 12 ohms, 4 ohms. For t greater than 0, this switch is open. 2 ohms, and as t goes to infinity for constant values, the inductor looks like a short circuit, and this is I of infinity, which can be found just from a current divider. So this is 4 amps times 12 ohms over 12 ohms plus 6 ohms, which is 8 over 3 amps.